All right, so thanks for turning in your assignments yesterday through Teams. I know there are some of you who have not had a chance to turn those in, so you can still turn in. The assignment is closed in Teams, but you can still turn in through email or through Remind. You still get an A for the assignment if you can get that into me. So if you get that in sooner than later, that way you can just focus on the next set of assignments, which is going to be due the following Wednesday. So assignments 6 through 10 will be due the following Wednesday, and then the following Friday will be the remaining assignments 11 through 16. Okay, so we're going to finish up on worksheet 1. We didn't get very far past limits, so let's go to worksheet 1, explore some of these derivative problems, multiple choice. Okay, so worksheet 1, third page, number 11. Okay, let me read the problem here. We have function above shows the graph of function g, that's the curve that you see here, and the line tangent to the graph at x equals -1. So the line is tangent to the curve at -1. Let h be the function given by h of x equals e to the x times g of x. What is the value of h prime of -1? So we want to find h prime of -1 from this h of x equation that's given to us. So before we can find h prime of -1, we first have to find h prime of x. So let's see what we can do to find the derivative. All right, so what do you see is involved if I want to find the derivative of this expression? Product rule, okay? So go through product rule here. There are my two terms there. There's my f and g expressions. G prime will be G prime. G of x's derivative is G prime. All right, so we have our derivative spelled out. Now we can work towards h prime of -1. Replace every x we see with -1. Okay, so we have the first parts filled in. Those are numeric values. We just have to find a replacement for g of -1 and g prime of -1 because our answer choices are not in function notation. So we have to go to our graph. What do you think g of -1 is? 3. Yep, that's just order pair, right? So we can pick that order pair directly off of the graph. Okay, how do you think we can find g prime of -1?
Formula.
Good. Good. So here they give us a very specific relationship between the line and the curve, and that relationship is the fact that the function g and the line are, or the line is tangent to the curve at -1. And whenever you have a line that's tangent, that means that not only do they share the same point, they also will share the same slope. So if I can find the slope of the line, even though I don't have an expression for me to find the derivative for g, I do have this line available for me to find the slope. If I can find the slope of the line, I also achieve the slope of the curve at that point. Okay. So conveniently, they give us two order pairs. So we can do change in y over change in x. -6 over 1 is just -6. Because the slope of the line is -6, we also can conclude that g prime of -1 is also -6. All right, we have the pieces that we need to enter in and find our slope value. Replace g of -1 with 3 and replace g prime of -1 with -6. Okay, do a little bit of cleanup, do a little bit of rearranging. I'm going to bring that e back down to the denominator. I'll make it 3 over e minus 6 over e. And that reduces to be -3 over e. Answer choice B. Okay, any questions so far? Okay, let's try number 12. Let's go to a calculator question here. So 12 says, let f be the function given by 3 natural log of 2x. G of x is x cubed plus 2x. What value of x do the graphs of f and g have parallel tangent lines? So let me highlight that here. F and G have parallel tangent lines. So if two graphs have parallel tangent lines, that means they must have the same slope. If they have the same slope, then we know that they must share the same derivative at that point. Okay, so what we're going to do is we're going to find f prime and g prime. Because we know f prime and g prime is where information about a function's slope is found. And we're going to set them equal to each other. And then we'll solve for x. So because we want to find a location where f and g have the same slope, we know we're going to dig down to f prime and g prime. If we can set them equal to each other, then we can figure out a location where these slopes are going to be equal, are going to be exactly the same. Right, so we're going to gather some information here. We're going to find f prime, we'll find g prime, and then we can set them equal. So here's f of x. Here's g of x. Okay. We have to find the derivatives for each separately. We have a rule for natural log of u. The derivative for natural log of u is just u prime over u. So as you guys are using these formula sheets, try to begin to work towards committing them to memory, so that by the time May 4th comes around, you feel like you've got a good handle on most of these formulas. Okay, u prime over u. Keep the 3, and then we have 2 over 2x. Okay, which cleans up to be just 3 over x. Okay, let's find g prime as well. This is 3x squared plus 2. Now that we have the slope formulas, we're going to set them equal to each other, solve for x, and then find the location where they're going to have the exact same slope. Okay, so this is not something that we can factor and solve by hand. We're going to have to rely on our calculator. So 36 Pro, you can use NumSolve, but on my graphing calculator, I'm going to bring everything over to one side, get a 0 to show up. That way I can just graph the expression and then simply search for the x-intercept. Okay, so here's my calculator. I'll go to y equals 3x squared plus 2 minus 3 over x. Sometimes it's you may have to kind of play around with the window so that you can get so that you can see where that x-intercept is going to occur. I do want to point something out here. I think this is going to be something that hopefully maybe take advantage of, especially on multiple choice sections, and you're dealing with the calculator and you're trying to graph a particular section. Look at the answer choices, okay? Because the answer choices is going to give you a range of values. And if you can just adjust your window so that you can see your entire range of values, but you don't want to go too far beyond it, right? So here, this helps me indicate to me that I don't have to go from -10 to 10 for my x. It's good enough if I just go from like -2 to 2, right? Because then I'm zoomed in enough, but I still have room where I can see all my potential solutions or my potential x-intercepts. So I'm going to go to my window, and based off of these values, I know that I'm going to be centering my values around these numbers. So the smallest value I see is around -1. The largest value I see is 1. So to give myself just a little bit of space outside of those intervals, I'll go from -2 to 2. And then the y value, this is just kind of arbitrary. I see that all these are decimal values that are really close together. So typically, I'm going to let my y value be a little closer as well. I'm expecting this graph to be kind of zoomed in a little bit more. So, but I think it's just a matter of playing with values. Now, if you play with your values here, only play with x min, x max, and your y min, y max. Don't touch the x scale. Those will just always be 1. Okay, I'll hit graph. And it looks like I'm getting a pretty good read. Should be pretty easy to trace to find that x-intercept. So go to second trace, choose option 2, which will find the x-intercept for you. And then you're going to use your left and right arrow button, pick a point to the left of the x-intercept, hit enter. and then scroll to a point on the other side of the x-intercept, hit enter, and then it'll find that x-intercept for you. You should get 0.782. Answer choice D. Any questions with number 12? Right, number 13 is similar, so I want you guys to be able to practice that on your own later when you're working on your homework. Okay, let's go to the back page. Let's go to 14. So 14 says, let f be the function defined above. Oh, by the way, this type of problem is pretty common, pretty popular on AP exams. So I want to make sure that we understand the concepts behind it. And it's not hard, but it's just there's a certain step that we have to follow for these types of problems. It says, let f be the function defined by this piecewise function where c and d are constants. So that's something to point out, is the fact that we have two missing pieces of information. Okay, we have two missing values to look for. If f is differentiable at x equals 2, what is the value of c plus d? Okay, this is also an important concept there to work with. F is differentiable. That means we have a smooth curve. Okay, so, but there's actually two things that I want us to be able to gather from this word. The fact is that this is going to be part of a smooth curve, but it's also continuous. Okay, and the reason why they don't say continuous and differentiable is because if they just say differentiable, then we know it has to be continuous. But I'm just going to write those two properties out. It makes it easier for us to work with them. So the fact is that these piecewise functions are not only going to connect, meaning there are no breaks from one graph to the next at 2, but also it must connect in a way where it's a smooth curve. And we're going to apply these two properties to allow us to create two equations, and then the two equations are going to be helpful for us to solve for these two missing values. Okay, so you don't have to draw the graph, but I just want to kind of give you a visual connection to this problem. So if you think about cx plus d, that's just a linear graph, right? X squared minus cx is going to be a curve. It's going to be a parabola. So imagine this. You have a graph that is to the left of 2, that's cx plus d, and you have another graph that is x squared minus cx, but they're going to connect in a way where there's no gaps from one graph to the next, but also it's going to be a smooth transition. So what that means is, because the graph is continuous at x equals 2, we can set the expressions equal to each other because they must share the same y value. And then on top of that, we can also say something about their derivatives, because it's a smooth curve, smooth transition from one curve to the next. That means we can set their derivatives equal to each other, because at x equals 2, they must also share the same slope. Okay. Let me put that additional step here. So at x equals 2, they're going to share the same y value. At x equals 2, they're going to share the same slope. So this is going to be how we're going to be creating our two equations that we need. Okay, so we know at x equals 2, I can set the two expressions equal to each other. And if it's at x equals 2, I can replace all the x's with 2 and see how far we can get. Combine the c's together. We have 2c plus 2c is 4c. All right, so we're kind of stuck because we have two missing values. We can't solve for one without the other one still being there. So we're going to take a pause on this equation. We'll come back to it. But this is where we need a support from the other equation that we're going to create. We're going to find the derivatives, set the derivatives equal to each other, and that will give us another way of gathering information about one of these missing values. So we're going to find these derivatives. Remember, c and d are constants, so you're going to treat c and d the same way that you would like a 5 or 3 or 8. So let me ask you this. What's the derivative of cx? C. Okay, what's the derivative of d? 0. Good. All right, so we know cx plus d just becomes c. That's good. The d drops out, allows us to hopefully isolate c and solve for c. Okay, the second piecewise, x squared becomes cx becomes c. Okay, so 2x. And we also know that this is going to occur at x equals 2. Okay, so there we have it. We can solve for x. Sorry, we can solve for c once we enter 2 in for x. Add c's together, I get 2c is equal to 4. Divide both sides by 2. Okay, so we have c figured out, which is good because we can use this to help us figure out the d in the other equation. So now I can say 4 times 2 plus d is equal to 4. Subtract a from both sides. 4 minus 8 is negative 4. Now I have my c and d value. I can just provide the answer because it's asking for the result of c plus d. C is 2, d is negative 4. So the result is negative 2. Okay, any questions with 14? 15, 16, 17. 15 is just rate of change, so that's just slope. 16 is tangent line matching the slope, so that's just finding slope as well. 17 is tangent line equation. Normally, you're given the order pair and you figure out the slope and then do point slope, do the derivative. Now 17 is a little bit different where they give you the slope, you have to work backwards with the derivative to get to the x value. Once you get the x value, put it into the original equation to get the y value, then you get your order pair and then use your order pair and slope to do point slope. Okay, but I want you guys to try those on your own when you're working on your homework. So 17 is another calculator question. I want to finish off this page with doing a review of implicit. So let's go to number 18. Okay, number 18. If 3x squared minus 4xy is equal to 1, then when x equals 1, dy dx equals. All right, we know we have to involve implicit because we have y's kind of mixed into the equation. It's not just y equals on one side and everything else on the other. So we definitely know implicit is involved here. What else? What else do you see we have to use? Good, product rule. You see x and y are being multiplied together, so we have to involve product rule as well. Okay, so I'm going to jump directly into my derivative step here. 3x squared becomes 6x. going to keep track of that negative for later when I distribute. So let me bracket off my product rule term, my product rule steps here. So f prime g plus f g prime All right, so going down my derivative here, at 4x becomes 4. G is just my original y. 4x stays. And then g prime. G prime is y's derivative. The derivative of y is 1, but this is where dy dx shows up. Equals, careful, the 1 is a constant. It doesn't stay 1. It needs to go to a 0. So good. We have our derivative. We just have to get it down to solving for dy dx and getting down to a numeric value. I like to just go ahead and fill in the values now so I can just solve for dy dx. But do I have everything that I need to get a numeric value out of dy dx?
No.
Okay, what's missing?
The Y.
The y, right? So ideally, the problem would be nice to just give you the full order pair. But here, they only give you the x value, so we have to spend additional effort to get to the y value. So what can we use to get to that y value?
The original.
Yeah, the original equation is how we're going to get order pair. So we're going to enter 1 in for x. We can solve for y. Once we have y, then we have everything that we need to enter in and solve for dy dx and get to a slope numeric value. Okay. So I'll enter 1 in for x and see if I can solve for y. So if I subtract 3 from both sides, I get negative 4y is equal to negative 2. Divide both sides by negative 4, I get y is equal to 2 over 4, which is 1/2. So now I should be ready because I have my y value, I have my x equals 1, and now I can enter all this in and solve for dy dx. And while I'm doing that, I'm also going to distribute the negative through. Combine like terms, 6 minus 2 is 4. Divide both sides by 4, I get dy dx equals 1. And that's my slope. I left another implicit differentiation problem for you guys to try for practice purposes, but we kind of hit a little of each topic from derivatives unit. So now let's move on to worksheet 2, where we're going to explore the second half of first semester topics, such as related rates, curve sketching, particle motion. Okay. All right, anybody still need to look at 18? All right, let's go to worksheet 2. Yeah, it's been a while since we've seen related rates, so let's review these types of problems. So related rates, usually they are in kind of a word problem format, and we know that time is always the independent variable that's impacting every part of our equation. So we're going to be expecting some d over dt to show up. Whatever variable is in the problem, that's what the d over dt is going to be in reference to. So number 1 says the radius of a circle is decreasing at a constant rate of 0.1 centimeters per second. In terms of the circumference, what is the rate of change of the area of the circle in square centimeters per second? So let's gather some information here. We have the radius of a circle. We know r for radius, but it's decreasing at a rate of 0.1 centimeters per second. So I know that this is not going to describe, it's not a static value. It's going to be involving a rate. So I know this is going to be dr dt, right? Dr dt is what we can assign this value to be. But we also see the word decreasing, so that indicates that we have to adjust the sign of that 0.1 to be negative. In terms of the circumference, what is the rate of change of the area of a circle? So we know we have to involve area of a circle and circumference of a circle. I'm just going to go ahead and write those formulas down. A equals pi r squared, C equals 2 pi r, and we're looking for the rate of change of the area of a circle, so we know that we're looking for dA dt. All right, so that's everything that the equation, that the problem references, and then we can go from here. These equations, we need to make sure that we know that we memorize, because these equations are not going to be given to you on the AP exam. I forgot to put the circumference formula on your formula sheet. So if you want to add that there, circumference under the area of a circle, you can say C is equal to 2 pi r. But I also want to point out something here. If you know the area of a circle, and let's say you forget circumference, you can get to it by simply taking the derivative. If you do power rule, pi r squared, if you bring down the 2 in front, it becomes 2 pi r. So there's that derivative relationship there, where if you know the area of a circle, you can just arrive at the circumference without having to, in case you forget it. All right, so hey, we know we have to work our way down to dA dt, so I'm going to go ahead and find each of these derivatives, even if I may not need both derivatives, just so that I can have it in front of me. A becomes dA dt. Pi r squared, we're going to have to find this derivative, so pi r squared becomes 2 pi r times what? What else do we need? Good. So every variable is impacted by time, so we have d over dt for every variable in the equation. Okay. Maybe I don't need dc dt, but just for us to practice writing it down here, dc dt, or c becomes dc dt. And what's the derivative of 2 pi r?
It's 2 pi.
Okay, 2 pi and dr dt. Good. So even though the r disappears, we are asking for r's derivative, so that's where that dr dt comes up. Okay, so we have dA dt show up. We're just trying to figure out what is the rate of change of the area of a circle. And we wanted to match one of our answer choices. I can make some substitutions here. I know that dr dt is that negative 0.1. It says in terms of circumference C, so how can I involve circumference in my answer? What do you know about 2 pi r?
Oh, you could just substitute it for C.
There we go. That's how we get to our answer there. Circumference is 2 pi r. We just make that substitution, and then it matches the form that our answer choices are in. Okay, number 2 is similar to number 1, so have you guys try that on your own. Let's look at number 3. Okay, if the base of a triangle is increasing at a rate of 3 inches per minute, while its height, h, is decreasing at a rate of 3 inches per minute, which of the following must be true about the area A of the triangle? Okay, we know that we're dealing with area of a triangle. We have some information about the base and the height, so let's see if we can assign those, assign to their appropriate variables here. So we have base B increasing at a rate of 3 inches per minute. And then we also have H, which is decreasing at a rate of 3 inches per minute. So let's see if we can assign those here. So base B is increasing at a rate of 3 inches per minute. What variable is that referencing?
Like DH over DT.
Mm-hmm. That's for H, but for B it'll be dB dt, right? Okay, so dB dt, we can assign that value. Increasing at rate of 3 inches per minute, so what do we want that to be? Positive, good. So positive 3 inches per minute. The height is decreasing at a rate of 3 inches per minute. So dH dt is negative, right? Right, which of the following is true about the area of a triangle? Let's create our area of a triangle formula. Area is 1/2 base times height. So I know I have to probably work my way down to the derivative, otherwise I'm not going to be able to get that connection between area and these rates. So if I want to find the area, if I want to find the derivative, I need to produce dA dt, but to produce dA dt on the right side, I have to involve what? Product rule, yeah, product rule again. All right, so f prime g plus fg prime. All right, so 1/2 b's derivative is just going to be 1/2 dB dt, right? B disappears, but we're asking for b's derivative, so we have that dB dt. Times h, back to f, and then h's derivative is just dH dt. Okay, so we're going to insert these values in and see where we are after that. Okay. Replace dB dt with 3. Replace dh dt with -3. Okay, we don't have h and b, so we're just gonna have to hold on to them. Okay, so I'll say dA dt is equal to, I'm going to combine some of this together, make it a little bit cleaner. I'll make it 3/2 h. And here I'll make it -3/2 b. Okay, this is as far as we can go numerically or formula-wise. So I'll put a box around this, and let's go to our answer choices and see if we can make some conclusion as to what's happening here. Or it says, which of the following must be true about the area of a triangle? So dA dt represents the rate of change of the area of a triangle, right? If we have a positive dA dt, that means area is increasing. If we have a negative dA dt, that means area is decreasing. We don't know what h and b are, okay? So we can just insert with any value that we want. It says A is always increasing. Is this always going to be true regardless of what h and b are? Not always true, right? Because we can find situations where we can force this rate to be negative, right? As long as the b is greater than h. Okay, so A is always increasing. That's not always true, not especially if we can choose our h and b value. A is always decreasing. Okay, not always true either, right? If h is greater, then that's scenario's out the window. A is decreasing whenever b is less than h. So when b is less than h, are we going to be able to get a negative dA dt?
No, it's only increasing when b is less than h.
Good, right? So C doesn't quite work. Looks like we're getting closer here. A is decreasing whenever b is greater than h. Yes, right. So the nice thing is that they're both share the same coefficient, so we can just compare apples to apples here. If b is greater than h, that means the negative is going to be greater than that this positive value, which is going to force this dA dt to be negative. So D is our answer. A remains constant. We know this isn't true because that means that dA dt is always 0. But dA dt is only 0 if your h and b are the same, and we can't guarantee that h and b are always the same. So, okay, so this is one of those problems where you get to the answer, but it's still not the answer. We still have to do some interpretation to be able to get to the answer choice. So adds another layer of complexity to some of these multiple choice questions. All right, number 4 is more of a standard related rates problem. I think you guys can get through that on your own. One last problem that I want to do in class is number 5. So let's go to number 5. We'll finish up related rate section, and then we'll do curve sketching next time. We'll do that tomorrow. Okay, you may recognize this. This is a similar triangle problem involving shadows. So this is one of those shadow problems that we've seen in the past. So a person whose height is 6 feet is walking away from the base of the street light along a straight path at a rate of 4 feet per second. If the height of the street lamp is 15 feet, what is the rate at which the person's shadow is lengthening? So we can kind of create a triangle out of this, a triangle within a triangle. So I'm going to just draw a separate diagram and refer to it. Okay, so these problems are always going to be set up where you're going to know the heights of this triangles. So we have the height of the person being 6 feet. And then we have the height of the lamppost, which is 15. And you're always going to set up splitting up those subsections on the horizontal side as X and Y. Okay, we're going to set up proportions using similar triangles. So you guys see these two triangles. You got a triangle within a triangle. I'll highlight the big one in yellow. So we're going to set proportions here. We'll say the height of the small triangle is to the height of the large triangle as the base of the small triangle, which is y, is to the base of the large triangle, x plus y. Make sure you don't say x over x plus y, that you say y over x plus y, because x doesn't represent the full base of any triangle, right? It's the y that's the full base of the triangle. Okay, so that's our equation. What we're going to do is we're going to do cross product, clean the equation up, combine like terms, and then we'll find the derivative, and that's where the d over dt will show up. Distribute the x through, distribute the 6 through. Combine like terms, subtract 6y from both sides. And now we're going to find the derivative. Okay, so these are this equation is easier in the sense that there's less messiness, but we just have to know how to set it up. We're going to produce dx dt and dy dt out of this. So 6x becomes 6 dx dt. And then 9y becomes 9 dy dt. Okay, let me define what each of these represents, what each of these derivatives represent. So dx dt represents the rate of change of the person walking. It's basically how fast a person is walking. We also have dy dt. dy dt represents how fast the length of the shadow is increasing or decreasing. And finally, this is not part of this problem, but it may show up, is what happens if I add the two rates together. So the person walking and the length of the shadow is going to contribute to how fast the tip of the shadow is moving in relation to the ground. So if I add the two rates together, it'll tell me how fast the tip of the shadow is moving. Okay, so from here, we have our equation. Let's see what information they give us. They say that the person is walking away from the lamppost at 4 feet per second. So we know this distance is getting larger. So we know dx dt is going to be 4 feet per second. And it's asking, what is the rate at which the person's shadow is lengthening? So really, we're just trying to find dy dt. Well, I think we're almost there because we have dx dt, we have the equation, and if we simply substitute 4 in for dx dt, we can solve for dy dt. If we have dy dt, we have the rate of change of that length of shadow. Replace dx dt with 4. Divide both sides by 9. We get 24 over 9. Use your calculator to reduce that to get it to match one of the decimal answer choices here. .667. Okay, that's our answer choice. But if I want to extend this a little bit longer, a little bit, let's say if it was asking for the rate of change of the tip of the shadow, then if I want to find the rate of change of the tip, I'm just going to add the two rates together. Let's say there was a second part to this. So that's 6.667. Okay, I know the problem didn't ask for it, but just wanted to connect all the parts of this problem together. All right, so tomorrow we'll finish the rest of worksheet 2. We need to do some curve sketching. We need to do, I want us to be more comfortable with the calculator in terms of gathering information about the derivative graph, and then hopefully we can also have time to start on our third worksheet, which is more second semester material, like second theorem, first theorem, area, volume, differential equations, okay? All right, thanks everyone. Hope you guys have a great day. See you guys tomorrow.